Hello everyone. Hope all you are doing good and all you are safe, most importantly. And as we know, we are at the stage of unlock 2. So we have to be safe, keep in mind, and take the proper precautions and take care of your family members too. Okay. So let's start today's topic. Today I have picked an important topic which is MBBEFD statistics, which is basically from statistical mechanics. Here first we will discuss the comparisons, the differences of those three statistics, and then I will show you an example, and through it I will compare those three statistics. Okay, so let's start. Here MB statistics, B statistics, and FD statistics are there. In that table, I have mentioned all the differences. Minimum 5 differences I have discussed, but in your exam, 3 can come only. For 3 marks, it will be there, and you have to mention 3 differences only. So, at the first point, for MB statistics, particles are identical. Keep in mind, particles are identical for each of the statistics. Those should be identical. That means structure wise, shape, size, the particles should be identical for those three types of statistics. Okay. Then what is the difference between them? Basically, they are distinguishable for MB statistics, and after that, they will be indistinguishable for both the statistics which are BE and FD. What is BE and FD statistics? First, let me tell you one thing. What is MB, BE, and FD statistics? MB stands for Maxwell-Boltzmann statistics. BE stands for Boson-Einstein statistics, and FD stands for Fermi-Dirac statistics. Okay. So here you need to learn that for MB statistics, which type of particles are included only. For only the classical cases and classical particles, we use MB statistics to describe the distribution function. And for BE and FD, we use quantum mechanics. Basically, those two statistics, that means BE and FD statistics, are entirely from quantum mechanics because they included the spin only. Okay, so at the second difference, they do not possess any kind of spin. That means no spin is there, and whenever spin is 0 or integral spin, see, S equals to 0, spin equals to 0 is also another kind of spin. Okay, and whenever it is half integral spin, then it is included into FD statistics. Okay, now, at the point 3, the particles do not obey Pauli exclusion principle. Acha, what is Pauli exclusion principle? Pauli exclusion principle states that at each state there will be only one particle. Okay, that means in a state only one particle should be there. That is basically Pauli states. Okay, whenever it is not obeying Pauli exclusion principle, that MB statistics, that means in one state number of particles, that means more number of particles can be occupied. Okay, now BE is under quantum mechanics, still it is not obeying Pauli exclusion principle. That means in each state there ABC are the particles. In a state, 3 or 4 or more particles can be there in one state, one single state. And for FD statistics, they obey Pauli exclusion principle. Okay, that means for FD statistics, only one state carries one particle. Okay, now coming to the point 4. That is, the particles follow MB statistics are called basically classical particle. I told you that in the classical field we use MB statistics, and for BE, that means boson-Einstein statistics, which particles are following these B statistics, they are called bosons. Okay, and for FD statistics they are called fermions. Okay, because the name of the scientist is Fermi here, Fermi Dirac, that's why fermions. And for BE, boson and Bose and Einstein, the name of the scientists are like this, and that's why the particle name is like this, bosons. Now, the example of MB statistics actually is gas molecules. Why? Because we treat gas molecules as classical particles. That's why the example of MB statistics can be written as gas molecules, and another aspect I can say. In BE statistics, photons and phonons are included here, and because photons and phonons are having only spin 1. For photons, spin is 0, and for phonons, deuterons, spin is 1. That means integral spin is there. Okay, that's why they are called bosons. And protons, neutrons, and in electrons, those are half integral spin. Basically, the spin of those nucleons, that is protons and neutrons and electrons, are having the spin half. That's why those are called fermions, and those are basically obeying FD statistics. Okay. So here, this is an example, and we will consider a case, and by which I will show you where and at which point those three statistics can be applied. Okay. So here I have written some points. Basically, suppose we have a gas of n identical point particles. I told you for those three types of statistics only, particles should be identical in a box of volume, which is volume is V, and then we say when we say gas, we mean that the particles are not interacting with one another. Whenever it is not interacting, that means non-interacting particles are there. Then which type of states, which type of statistics we will apply? Basically, suppose we know the single particle states in the gas. Okay, we would like to know what are the possible states. Whenever we need to know the possible states of the system or the distribution function of the system, how the states are arranged, basically, then only we need those statistics, which is MB, BE, or FD, that we need to learn. Okay, what type of statistics we will apply, basically. So there is an example. So let's start. Let's consider a very simple case, which is basically we have only two particles. We have only two particles in a box, and that box should have some states only, and the number of particle states is 2 only. So here we have to find out how many distinct ways can we put the particles into these two states. Two states are there, and where and how we will put those particles, and how many ways are there. Okay. So here Maxwell-Boltzmann statistics is there, and now we will find out this case first. So first I have just written that this is a classical case. I told you that for classical field only Maxwell-Boltzmann statistics is used. So in this case, particles are distinguishable. I told you in the difference table, and here we are labeling those particles A and B. I told you, and let's call two single particle states at 1 and 2. So here one state and two states are there. Okay, and how they should be arranged? So we can put those two particles at one state, that is at state 1 also, and at state 2 also. So two states are there, and again we can put each of them in the each of the particle state A, B, and BA. So totally we have 4 distinct ways for Maxwell-Boltzmann statistics. Okay, now for boson-Einstein statistics, here you need to remember what kind of particles it should be. It should be indistinguishable. I told you in the first slide that for boson-Einstein and Fermi-Dirac, the particles are indistinguishable. Then that means we cannot differ those particles. That means we cannot label those particles A and B. We have to label those particles same. So both the particles are A here. Okay, and you have two states again, 1 and 2. So now how will you put those particles? How many ways should be there? So here in each state you can put both of them in each state, and again in state 2 you can put, and again another state is there, which is you can put A at the state 1 and another A at the state 2. So basically how many ways are there? 3. Total number of ways by which you can arrange those particles in the state in the possible 2 states are basically 3. So 3 states of the system as a whole, and 2 by 3 states have the particles bunched. Why 2 by 3? Because among 3 states only two states are there at which particles are bunched. See, at the state 1 double A is there, and that at state 2 double A is there. So basically among 3, wait a minute. So among 3 there are 2 states at which particles are bunched, and there are 1 state at which particle is in separate state. Okay, got? Now Fermi-Dirac statistics. This is another quantum mechanical case I told you, and for this also particles are indistinguishable, and both the particles are labeled as again A. So here another thing is there, most important thing for Fermi-Dirac statistics. What is it? They basically obey Pauli exclusion principle. Okay, they basically obey Pauli exclusion principle, and that is most important thing for FD statistics. That means, what does it mean basically? That means one state only carries one particle. Okay, so that's why state 1 carries only A and state 2 carries only A. So there will be no state where the particles will be bunched up. Okay, so basically only one single state is there for FD statistics. So that's why we have written that we get a total of one state of the system as a whole. None of the states have the particles bunched up, and the Pauli exclusion principle forbids that. Okay, so this is it, and I think this kind of comparative discussion will be helpful for you to understand those statistics, the MB, that means Maxwell Boltzmann, Bose-Einstein, and Fermi-Dirac statistics, at which point and how we will use them, that I have discussed now. Okay, in the next lecture I will pick up some another topic from statistical mechanics again. So till then, thank you, bye bye.